So anyway, so it's 3 o'clock. So welcome everyone who could find time for this really interesting presentation from Thorsten Garlich, our former colleague at Wintershall, now representing Geolog International. And he will have a very, very good and interesting talk about geochemical production allocation. And the main author of this is himself, Thorsten Garlich, and also colleagues from Geolog Placido, Franco, and Roberto Galimberti. And as I explained to you that you can write your questions in the chat, and then also at the end of the presentation, you can raise the hand and then you can ask your questions. So I mute myself and switch off my camera, and Thorsten, the floor is yours. Welcome.
Yeah, thank you very much, Balázs, for the introduction. And thank you for giving me the chance, or Geolog the chance, to present. So today we will talk about the geochemical production allocation, and we will show you a case study from Norway. As Balázs said, this is a huge contribution from Placido, Umberto, and Roberto. We need to start with a disclaimer first. So all information you see here, material, figures, data presented, have been shown before in different occasions on these 3 main references. And you see today more or less a synthesis and a story out of these results we presented already before. All other figures and data are according to the references. Data and analysis are older than 2 years and therefore considered as historical data. The study was conducted with Wintershall, Norway, and Geolog as part of a research project. I left Wintershall, as Balázs already said, and I'm not longer an employee for Wintershall or any related company. I am now a full employee of Geolog International. For many people, Geolog International, this is real-time service logging during drilling, and we concentrate now with our research and laboratory called Geotech on post-well analysis and services. This is the building you see. This is our lab located in Milan, Italy. What can offer Geotech as a lab services is a very small overview. On the left side, the exploration geochemistry, the source rock evaluation, water, oil, and gas analysis for source oil correlation and later oil-oil correlation. We also offer the biomarker analysis for source rocks, fluids, extracts, and also trying to identify the fluid migration preservation and link it with XRD or XF data in chemostrat analysis. Today, we will concentrate more on the right side, the reservoir and production geochemistry. Here, the main topics would be reservoir fluid heterogeneity and similarity, reservoir characterization, compartmentalization, and formation continuity. The production allocation of commingled fluids, and this is the main talk of today, for defined end members, and more important, over time, adding the time dimension. This is the time-lapse geochemistry. The agenda for today, we will go a little bit to the geology and the general overview of the case study area, and very rough and high-level overview of the geochemistry and the petroleum system. The main focus is then today on the production allocation. Again, a little bit storytelling, why we did it, what is the sample set for the production allocation, and what is the case study historical background, so which phases we are running through. And at the end, we will go through the main phases. This was the feasibility study. Here we analyzed end members. We will show the results, lessons learned, and then we started with phase 1 and phase 2 production allocation. And the presentation will end up with a small summary. Our introduction. Today we talk about the Maria field. The area is the Norwegian continental shelf, the Norwegian Sea, and we talk about the Haltenbanken area. Exploration drilling at the Haltenbanken area started in 1980, and the major structural elements in the Haltenbanken are from east to west: the Trøndelag platform, the Gimson Basin, the Halten Terrace, and then the Sklinna Ridge. Our field is a Maria field, as you see here highlighted, and also zoom in from the NPD fact pages, the Maria field, and in the south there's a Trestak field, which comes more important a little bit later. The Maria field is located on the Halten Terrace in the Norwegian Sea, roughly 25 kilometers east of Christine field. The Maria field was discovered in 2010 with 3 exploration wells in total, and the plan for development and production was approved in 2015. The field was initially being developed with 2 subsea templates tied back to the Christine field. That's also the reason why we focus on the Christine field mainly. The production started then in 2017 and is today expected to continue until 2040. The water depth here is roughly 300 meters. The reservoir is at a depth of 3,800 meters approximately. The field produces oil and gas from 6 sandstone packages and containing some shales and layers. And these are mainly coming from the Middle Jurassic Garn Formation. The thickness of the reservoir is roughly 90 to 100 meters. On the right side, you see more or less the location of the Maria field in the Norwegian Sea and next to Norway. The Maria field is located in the central western sector of the Halten Terrace. You see that on the left side here again. There is the black bar highlighting the cross-section you see also on the right side. Here we have the corresponding to a tectonic horst. The Maria is a horst platform and a footwall high, respectively. A lot of the field in this area is elongated in the general north-northeast, south-southwest direction. This is, for example, Chestag, Marias, Mørburg, Bergknapp, Christine, reflecting the major control based on the north-northeast, south-southwest trending fault zones and consequent block rotation. This is typical for the Halten Terrace. The Maria field itself is a quite flat lying horst block, 11 kilometers by 3 kilometers, and you see that here this is quite flat in the area. There was another nice publication from Bunkert et al. They published a very regional Cretaceous, base Cretaceous structure map. Here you see again the quite flat structure of the Maria field. It is very prominent, the horst block coming out, and here's a potential connection towards the south to the Trestag field. The Christine field is somewhere here next to Maria field. So the one thing we can add here as well is the potential kitchen areas are grams along surrounding the fields. And now we go also to the petroleum systems analysis for the Maria field. On the right side, you see the main source rocks is the speck formation or Melke formation. The reservoir is the Garn formation for the Maria field. So not only for the Maria field, but in many other fields in this area, the speck formation and Melke formation are the main source rock. The reservoirs are either here in this Maria field, the Jurassic Garn formation, but also other formations are potential as a reservoir traps. The Garn formation for the Maria field is a single formation. There's not other formations for the Maria included. In the area, also seen here and highlighted here, there are other reservoirs present, so mainly Jurassic and Cretaceous sands. The seal, especially for Maria, is a speck and Melke itself as a seal rock. The overburden is then the entire package of the Cretaceous until present day position, and this is in Maria roughly piling up to 3,500 meters in thickness. The charge started somewhere 110 to 100 million years ago before present. The charge direction here in the Maria field is assumed to be from south to north. The next slide, we just have a very short look on the source rock. So the speck formation as a main source rock is a very good and excellent source rock. You see that on the TOC plot and the production potential. The speck formation is a classical marine oil-prone source rock type 2 or type 2,3S mixed kerogen type. So this is mainly the type 2 type. And then here we shift a little bit lower down with lower hydrogen index values towards the mixed type. The data you see here are the entire speck formation data from the NOD public geochemical database, and I filtered only to TOC values higher than 1% in TOC percent and also more than 400 degrees in Tmax. Some brief biomarker ratios. Here we use the Phyten NC18 versus Pristen NC17 plot. All the biomarkers are mainly in the mixed and transitional zone or more reducing marine zone in this part. All of them, or most of them, are in the early mature phase. You see that here. And on the right side, you see the wells and fields where we have data from the public database available. So here's our Maria field. This is then surrounded by Smørberg Sør, Bergknapp, Christine, Trestak, Durian Sur, and Durians Nord. One other deposition environment. So also here it's supported with mainly Maria and Bergknapp samples available from the database, that we are in a marine environment, and this is mainly linked to the Speck Formation source rock. One now more linked towards the field and area. Here the biomarker maturity for Maria and Trestak. As an example, this is used the DS terrains versus normal terrains in the TSTM ratio. Samples from Maria are these circles. They are very similar towards the Trestak samples. However, the Trestak samples are a little bit elongated, potentially a little bit higher mature, but there is already set a question mark. So far, it is assumed that the Maria is a little bit in total less mature. Therefore, the higher maturity is nearer to the kitchen area, the Trestak field. So the Trestak field was filled first, and then a fill to spill scenario is assumed that the Maria field is filled in the second. So therefore, it's less mature, further away from the kitchen area. Also, these data are from the public database, from the NOD. Following up this trend, so we have on the south the Trestak field. This has a little bit higher maturity. This is also shown by a little bit higher GORs, gas oil ratios. And when we go towards Maria, along the migration or along the fill to spill scenario, we end up in a little bit lower maturity compared to Trestak, but also the southern part of the Maria field you see on the right side, the Maria map, is a little bit lower mature, but the lowest maturity we see in the northern part of the Maria field. So there is a southern part, more or less the middle part, and the northern part, and this is having the same trend. We have a decrease in maturity and GOR. Therefore, based on the fill to spill scenario, we see that this also in Maria, the southern part was filled first, and then the northern part was filled second. However, as you saw before, we had quite high oil similarities. So this is still the case when you go to the biomarkers. The overall similarity is high. We have only small differences between the fields. These differences are mainly related to GOR and maturity. And within the fields, you also see a very small and minor trend from south to north. With this introduction, we go now to the production allocation. First, we talk a little bit about the motivation. Why should we do the production allocation and use geochemical fingerprinting? So geochemical fingerprinting quantifies the contribution of different wells, formations, or compartments to commingle production, adding an accurate allocation, optimization, reservoir management at very low costs. So you can say geochemistry analysis at this stage can always be done, and we will link it now to the life span of a field. So whenever you have the possibility and you drill and explore a field, you can take samples. When you appraise a field, you can take the next samples during the appraisal wells. When a development is planned, normally the development drilling is ongoing, you can take another samples, and then during production, of course, normally you have a wellhead and take samples again. So in all of the field lifespan, the geochemistry can help, and especially the production allocation can be very helpful in the production phase. But what is the geochemical production allocation? And here's one very important thing. The geochemical production allocation is a regular geochemical analysis to deconvolute the proportion of selected end members in a commingled sample over time. When you would erase it in a word over time, this would be only a reservoir geochemistry study. So the time dimension is very important for the production allocation. What can you use as commingled samples, or where commingled samples normally occur? When you have one well with multiple formations or pay zones, so these maybe are interesting to deconvolute in your field. There's one possibility that you have one field with different wells in the same formation, and this is the main case for the Maria field we talked today. Or you have just one platform with different fields, and you would like to deconvolute the different fields. How does it look like? For example, either you have formations in one field, you can also replace the formations with fields with one hub production. So this is always depending on your specific topic and things you would like to deconvolute. But you can also have one well producing from two formations, here elongated as an horizontal well from formation A and B. You take samples over time, analyze the geochemical fingerprint for them, and you can identify potential changes over time with the change in the contribution of these both formations. Now we go to the sample set for Maria. And here it is very important to say we have the perfect match for the production allocation because the samples are there. We had a lot of samples and samples and samples. And this is the dream for a geochemist talking about production allocation and the potential to use these sample sets. So not only the samples are available, but also the perfect end members we had for the samples. So we had single well tests or single well cleanups. And there's a huge amount of production samples taken over days, weeks, and months. So the production engineers collected a lot of samples and stored them. And this is the key for this success, for this story for Maria. And I have to say a very big thank you to the Maria team for this perfect sample set. They really collected it, made me aware afterwards, and I was able to use the samples. This is important. But what type of samples we have and why is it important, why we would like to do Maria production allocation is, of course, one or two other things important, not only the sample set. Maria has a very high similarity. So the high similarity is challenging. It makes this field difficult to deconvolute. We produce from only one formation. The geochemical data did not show a great unmixing when we use the biomarkers. They used mainly north and south. This was very good, differentiated, but within the wells, it was always tricky. However, which is qualifying Maria for a potential production allocation study, we have no alteration effects seen so far. And this was not so reported and also not seen by biomarkers. We have potential comparison with flow meters, so we can track record the geochemical allocation. And especially the wells in the south and north, they are very close to each other. So this is a very high interest to deconvolute the samples and also test the method of geochemical production allocation. So the perfect case for a research project. Maybe you ask yourself the question why we should use Geolog and Geotech. So I was in contact with Placido Franco when he was presenting in 2021 at the IMOX. This is the International Meeting of Organic Geochemists. And he showed that Geotech can do some geochemical fingerprinting. I learned that Geotech has a fully equipped petroleum and gas geochemical lab. Geotech methods were new at that time, unique and very cost effective. So I said that needs to be tested. Here in the lower part, you see the reference from Placido, and the main method from Geotech is highlighted here. So they use, and we use now, gas chromatography coupled with a mass spectrometer for alkylbenzenes. So we have this similar advantage and same advantage as multidimensional GC methodology. We have very high data density. It is easy to include more components, and we can also potentially further develop in the next cases or different cases when you talk about, for example, very heavy oil cases. But we need to go back a little bit to talk about the analytical workflow. And here we first check the workflow for biomarkers. This is mainly familiar for a lot of geochemists. So this is me taking some rock samples in the core store in Norway. Normally with rock samples, either shales or sands, you can extract them. Sorry, and you have the heptane fraction. And you have your extract. The other thing is you can use your crude oil, and also your crude oil sample is normally then flashed with heptane. And the main reason why we would like to flash the entire hydrocarbon or the entire oil sample is to get rid of the asphaltenes. The rest, which is revolving, is the maltane fraction. The maltane fraction contains the saturates, aromatics, and resins or NSO components. And then you normally do the separation. And this is very important. Please remember that the separation step is already a fractionation of your sample. Of course, we would like to use the saturate fraction and aromatic fraction, which is coming out of the separation process, to run our standard gas chromatography for the different fractions, and also the GCMS and GCMS for biomarkers and age-specific biomarkers, or the compound-specific isotopes on all the fractions. So the separation effect, this is very important. This is in the Geolog method for production allocation, not present anymore. We use direct the fluid, so there's no fractionation effect. So we have more or less a direct fingerprint of the oil. So this entire whole crude oil is diluted in dichloromethane, and this direct dichloromethane is directly injected into the GCMS system to make the fingerprints. Normal cases, we will run 3 replicates analysis, and you have your chromatograms. After you have your chromatograms, we go to the data processing. What is analyzed? It is the acrylbenzenes and polyaromatic hydrocarbons. We generate or analyze 100 peaks and calculate roughly 300 ratios out of it. The ratios and the data, they are normally processed with statistics, and this is a very common approach in the geochemistry with principal component analysis, hierarchical clustering, and then for unmixing, we use the maximum likelihood estimation. This is one example for hierarchical clustering. This is another example for principal component analysis, and this could be one example for an unmixing of 3 different end members. When you are interested in the methods, you can use the article presented by Sandoval et al. In Fuel, an original deconvolution approach for oil production allocation based on geochemical fingerprinting. We go back and now know that we have a different new method. What is the case history for the Maria field? So the first step was a feasibility study with 5 end members, the so-called reservoir geochemistry. Here, Geotech and Geolog showed that they can deconvolute end members, and this is the proof of the Geolog methods. You can imagine this was a success, as I said, otherwise we would not present the data today. So the next step was set up a research project, and we test if this feasibility study, so just the deconvolution of the end members, is possible to use to deconvolute real production samples. And then in the last phase, there's also a second phase. The field further developed during the research project. There was another well drilled, and of course, this another well, based on the success we had in the first phase, we would like to include and make new production allocation samples with the additional well. On the right side, you see the sketch of the Maria field and the subsea templates. This is template H and G. The approximate travel time of the fluids from the templates, from the flow meters towards the platform is 12 hours. What type of samples we have available specific, not only that we have a huge amount of samples from the production team available, but here we talk about 3 exploration wells, and you see that on the right side on the map. This is highlighted with the stars. These are the 3 exploration wells. For the feasibility study, we used the 5 end members of the different wells. In the south, we have H1 and H4. In the middle part, we have H2. In the northern part, we have G1 and G4. This was the feasibility, and then in the phase 1, we added to the feasibility same sample set 5 commingled production samples. In the last phase, there was again the 5 production samples. Here we had cleanups. This is the main difference to the new sample. The new sample was not cleaned up after drilling, so we had a single well production, and we needed to look where the single well production for the new well is. At the end, we compared the end members with 9 commingled samples. So now we will go to the feasibility. On the left side, you see the Maria field. Now we go through the entire sections and will highlight well by well. On the top right part, you see the hierarchical clustering analysis, and this is based on the correlation between the samples. In the lower part, you see the principal component analysis. This is already presented 2003 by Placido, Franco et al. So we start with the first well. The first well is the G1, and you see the G1 in the replicates is plotting in the upper left area. You see the similarity of the samples in the hierarchical clustering. The main question is, can we deconvolute and separate the G1 in the northern part from the G4, which is coming here in? And we can. So the G4 is plotting or away from the G1, which is very important, and also from the cluster analysis, this is plotting away, but still together compared to the other samples coming in. The H2 is a middle well coming in here, and here we have also the part that this is between the sample sets. So this is the northern part, middle part, and then we start with the southern part. So the H1 is in the south coming in, and the H4. So you see 2 important things. We can separate the northern part internally, G1 to G4. The entire sample set is separated south to north, so or north to south, and also the middle part is separated. In the south itself, we can separate again the 2 wells from each other, H4 and H1. So you see more or less the nice results at the end, but what we learned in between in this feasibility study, this is the lessons learned, we learned here already. The conventional geochemistry, for example, biomarkers did not show a perfect separation for all wells, but they were very robust when it comes to south, mid, and north. So you can easily use also the biomarkers to deconvolute the southern part, the middle part, and the northern part. In the northern and in the southern part, deconvolute the wells, it was not so easy possible. So Geolog's method demonstrated a clear separation, consistently distinguished between the wells and with a high reproducibility. So you saw before also that we used replicates, and all the replicates are plotting in the same area. And this is also the main learning what we had when we talk about high similarities, how we overcome the similarities. This is mainly the statistics, and the statistics is very helpful and very important. So we run replicates, we see the replicates, how they drift in the instrument with a high similarity, and if we can deconvolute all the samples. Based on these results, the replicates was always from then on recommended to be used. The exploration wells, they were not a good fit. This is also one learning we had. So the exploration wells are too punctual. They don't allow a deconvolution with the production samples later on. In the lower part, there is a type Y. So the production well, when you have a cleanup, is producing from, for example, the entire red area, whereas your exploration well is potentially only have 1 or 2 samples very punctual in the middle part of this area. So you potentially lose the toe section and the top section in the geochemical signature. So for this Maria field, all the 3 exploration wells were not suited to use for geochemical production allocation. So we talked about a lot that we can deconvolute the samples. Now we would like to see the production allocation results. So for the project phase 1, I just have a reminder here. The multi-phase flow meters have a travel time of 12 hours from the flow meter towards the platform. So the flow meter is always in the past, telling you what is ongoing. And during the study we did, from my information, the multi-phase flow meters were not calibrated. You see on the first sample, this is not a good correlation. Maybe, and we think and we believe that here the travel time is very important. Here the timing of the sample, when you take the sample, is one key factor. How does it look with the next sample? So overall, with the next sample, we have a quite good fit. You see the color bars. These are the geochemical allocation, and the black dots, this is the multi-phase flow meter allocation. This is much nearer together compared to this first sample. You see that also on the right side in the table with some numbers. So these numbers are quite near to each other. However, it's not always 100% the same. The next sample here, we had potentially only 3 end members. The geochemistry showed us only 3 end members, and the flow meters showed also only 3 end members. So we have almost a very good fit with flow meters and geochemistry. The fourth sample, also here we see a quite good fit. There is always a small variation, and the main variation is coming into H2. So the middle part is a little bit higher contributing for the geochemistry compared to the flow meters showing us. And also the last sample shows a almost perfect fit between geochemistry and the multi-phase flow meters. But what is the right method? Is it geochemistry telling you the truth? Or is it the flow meters telling you the truth? Or both? This is one very important question. This is more rhetorical question because this may be unanswered during this presentation. But we were very happy with the results during that time. These were very excellent results we saw. There is, of course, a possibility to deconvolute the different wells from each other. With this excellent results, we said from the feasibility study in phase 1, we would like to add the new well. The new well during that time was drilled the G2 well, and this is coming in here. And these started then the second phase, and also these second phases already published. This was the last year's EAGE with Placido, Franco. Here we directly jump in the deconvolution of all the 6 end members. You see directly also here, we can easily separate the end members from each other. This is now a little bit shifted because we added a statistical new end member in it with the G2. But again, all the samples can be separated. And here we have H4, H1, the southern part, the middle part H2. The G2 is laying below here in the H4 area, and the northern part G1 and G4. Also from the hierarchical clustering, you see there is a good and clear separation between the samples. So again, we can separate all the samples from each other. And this is very important because now we would like to make a deconvolution again on these samples. Here it's a little bit more busy, this slide. We have on the left side again the field outline, all the wells. Now we don't go each sample by sample, we directly go to the full sample set. And you see on the bars, this is the same concept as before. We have the color code for the wells. We have then the black points for the multi-phase flow meters. You see in some cases, for example, the first sample, that we have no contribution from the geochemistry for one well. This is the H4 well, whereas we have a high contribution from G2. We have one sample which fits quite good. This is the M2 sample and the M4 sample. For all the other samples, you mainly see there is a huge gap between H4 and G2, and they are so close that the geochemistry in this method and deconvolution is not getting the 100% grip on it. Yeah, so it makes more complicated. We have now 6 members we would like to deconvolute, and this is getting tricky for this method. However, 1, 2 good results, and then another sample set, sample 6 to 9, we also have one, the half of it as a very good results, and especially the last sample is laying on almost on the spot that the multi-phase flow meters and the geochemistry are coming almost to the same results. The first 2 samples, again, you see a high contribution, much higher for G2 compared to H4. And here there's maybe a misallocation for both of them. Just as a one nutshell, we have a very good fit for 4 samples, and now in the 6th end member deconvolution. So the 6th end member deconvolution is quite tricky for the method. However, we believe we can easily deconvolute it when we go to a so-called 2-step allocation. So the 2-step allocation would be quite simple. We have the main contribution as before. We collect the data for H4 and G2 together in the first step. And then with the geochemical allocation, we try to deconvolute it in the 2nd step allocation. And this is a potential for the phase 3 and a potential to another presentation. But then there's again always the question. We are now comparing geochemical data with the flow meter data. Is it the right way? Are we doing the right? We're trying to mix or more or less fit the geochemistry with the multi-phase flow meters? Or is the geochemistry telling us something which is different and the flow meters are not showing us, for example, a cross communication between wells? This is also something we could consider and further investigate. With these, we are coming to the end. I would like to sum up the reservoir geochemistry, what we can do. So the reservoir geochemistry, this is the feasibility phase shown for the Maria field. Here we identify differences or similarities between different wells. We can differentiate between formations, fluids, and verify if they can be produced together. For example, if you have a very heavy oil and very light oil, this is also tackled normally in the reservoir geochemistry study. With the reservoir geochemistry, you define the field dimension, column heights, and compartments. So the reservoir geochemistry is very good to have a tailor-made development program, optimal wells and perforations, and you can save costs. The geochemical production allocation here is the quantification between or quantify the differences between wells, formations, and compartments from commingled production. Optimize your reservoir management and reserve allocation at very low costs. No production loss or well intervention for sampling at the wellhead or separator. So normally the flow is always ongoing. You connect sometimes a mini test separator, and with this mini test separator, you can easily get samples and the normal flow is not interrupted and you don't have any production losses. You determine flow between production and injector wells. This is quite easy, but you can also identify cross communication between wells. And this is again very cost effective, tailor-made for production allocation strategy. So in any case, also when you don't have the perfect sample set for Maria, it is never too late to think about production allocation, and you can always take wellhead samples to start with. The key learnings from this Maria project is what do you would like to separate from each other? Is it formations? So what is suitable to do the formation separation? Here you can normally use DSTs, MDTs, single formation wells, cleanups, and wellhead samples. And with formations, you have in many cases a quite strong separation or very clear separation. The differences is not so high as in the Maria case. But when you would like to do a well separation, like in the Maria case, Here we have also some suitable samples, and mainly depending on your setup, DSTs and NDTs are not so suited, for Maria at least. We always recommend to use cleanup samples because they are the first very initial production you normally take when your entire development well is drilled and you produce the first oil. So sample set is key, what type of samples you can take. So when you are in any development phase, please remember potentially in the future you like to use the oils for any production allocation. And then we almost be in the last slide. Thank you very much for your time. I have to thank Umberto and Placido for great help for the presentation. And I think I will go and give back to Balázs. Thank you very much.
Yeah, so very good talk, Thorsten. Really good overview of the method and the case study. So I think it's very good to have you to talk about these things. And it's very uncommon that all companies show such stuff or, like joint projects. So if anyone in the future from major operators like Equinor, BP, Repsol, Total, whatever, would like to show that is possible. You see, this was published 3 times before in different conferences and very good overview. But anyway, if any of you have any question, you can raise your hand. I don't see any question in the chat. Now we're not that many, 15 people, maximum was 20. And then you can just raise your hand and ask, and you have about 19 minutes, and at 4 o'clock we close. Anybody would like to try in their own fields this? Come on, people. Now you have the chance. Maybe Lloyd? No?
Yeah, I'll ask a question.
Yeah.
Lloyd Jones from APT. What was the spread of your internal standards on the PCA? Was that within error? Your PCA plots?
The PCA plots. You mean this, for example?
Yeah, so if you ran your internal standards, did they cluster very tightly? So the analytical error could be ignored?
Yes.
Yeah, okay.
For reference, we can add it for the next presentation.
Okay, cheers.
There is one question from Reza. Maybe you can speak up. There are not that many. Just unmute and ask.
Yeah, hello. Thank you very much. Very interesting presentation. I just have 2 questions. One of them is that I lost the link between this PCA. I think here is a qualitative deconvolution kind of, and later in the presentation was a percentage of a mixing, and I lost the connection in the middle. And the second question is that I think you use the biomarker ratios rather than biomarker concentration. So have you tried even biomarker concentration, and is that okay to use the ratios rather than concentration, or what is your opinion about it? Thank you very much.
Yeah, so the first thing is quite simple. Yes, the hierarchical clustering in PCA is mainly used to see how you can deconvolute statistically the samples. The raw peaks, peak heights are later on used in the, I will go back to the workflow. They are used in the unmixing algorithm. Yeah, so we use the peaks, heights, and ratios. They will be used, and in the unmixing it will be unmixed. So this is totally independent from the principal component analysis and hierarchical clustering. In this field, in the Maria field, we tested a lot, and also the biomarkers. The biomarkers either in the concentration with the internal standard, or the ratios were not suited. So they were not different enough to deconvolute the high similarity within the wells. When you talk about, and I will just jump back to one slide overview. When you talk about the northern part, the wells itself deconvolute G1 to G4 with biomarkers, what was unfortunately not possible, but the northern part as in segment or compartment is possible to deconvolute from the southern part, H1 and H4. But also here, in the southern part, the same as before, the H1 and H4, they are very close to each other, very similar in also the biomarker ratios. That's the reason why the biomarker ratios are not suited to make the deconvolution here. We tested mainly only the standard biomarker ratios. If there is any other biomarker ratios which are not in the standard NIGOGA guideline, this can be potentially tested, but we used the Geolog approach and geotech's analysis from Placido, Franco.
Thank you very much.
Yeah, I don't see any more questions in the chat, and I don't see any hands either. Are you sure that nobody wants to ask any good question now or try to do their own fields the same? Nobody? Then I don't think we need to drag it out till 4 o'clock. So I would say again, thank you very much, Thorsten, for this really excellent presentation of the also showing the Watermountain geology and main source rocks migration and case study and your method. And then I guess if any of you are interested in trying to set up any research, then you just contact them, and then lots of data from MPD, old wells, all freely available. And then basically, I would like to wish you a happy Easter. There might be one more course webinar in May, June. That would be more focusing on rifting and heat flow for extended margins. I'm not sure if we can do it. And then from September, we will try to continue with Christoph Kiedorf, who might take over from me the organizing role. So I guess, Thorsten, any final words, and then we close it.
No, thank you very much. Anytime you have questions, follow-up questions, please reach out and contact me. Thank you very much for the chance to present. And again, thank you for all the people involved for this study.
All right. Thank you very much. And congratulations for this very good talk.
Thank you very much.
And good holiday for all of you. Bye-bye.
Thank you. Bye-bye.